Friends, welcome to Meki Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement towards these kinds of wonderful videos and technical speak in the public domain. And next, I would like to thank my mentor, Professor R. Surendran from Government College of Technology for igniting a spark about creating a videos, technical videos in a public domain. And I would like to thank Almighty, my friends, followers, and my dear students and subscribers for their support and their views. Today's topic of interest is velocity and acceleration analysis. First, we are going to discuss about velocity analysis. Okay, first of all, what is meant by a velocity? So velocity is a vector kind of thing. The rate of change of displacement with respect to time is called as velocity. And acceleration, we have a rate of change of velocity with respect to time is called as acceleration. Let us give an example, broad example. If we are running a bicycle or a motorcycle at a speed, say a constant speed of a 30 to 40 kilometer per hour, so I am saying that 30 kilometer per hour it is called as a velocity, because in every time with respect to time it can complete 30 kilometer per hour, 30 kilometer distance per hour. It is said to be an velocity. If if you want to say an example of an acceleration, if I am running a motorcycle in a speed of 30 km per hour, if I want to complete the distance as early as possible, I ride a motorcycle towards from 30 to 50. Therefore, from 30 km per hour to 50 km per hour, the rise, the change in speed, change in velocity with respect to time, how much time to take the vehicle to attain 50 km per hour, that is called as an acceleration. And again, here if we want to speak an acceleration, we want to speak a deceleration. So what is meant by a deceleration? If I am running in a vehicle at 50 km per hour, if there is a damaged road or any traffic condition, if we want to slow down our vehicle, so I make my vehicle to 50 km per hour to 10 km or 20 km per hour at the span of a time, so that is called as a deceleration. So deceleration is a negative change of velocity with respect to time, whereas acceleration is the positive value of rate of change of velocity with respect to time. So with this example, I am going to start first velocity analysis. Okay, as we know that, as I said, velocity is the rate of change of displacement with respect to time, and the velocity, wherever the rotating or wherever the motion kind of thing is happen, definitely there is a velocity. Whenever a point change or a displacement is happen, there must be some velocity. Therefore, the velocity in machines can be determined by two methods. One is analytical method and another one is a graphical method. The velocity analysis deals with the graphical method, where in the graphical method the linear velocity and angular velocity are the very important kind. If we know the speed for the angular velocity, for a vehicle wheel, we say it as a front wheel, we have an speed of the wheel, say n rpm. We have an speed n, then we can easily calculate the angular velocity by means the formula 2 pi n by 60, where if we know the angular velocity we can find the linear velocity. Therefore linear velocity v is equal to r omega. And there is an interesting velocity is there, that is called rubbing velocity. Rubbing velocity is between two surfaces depends upon an angular velocity of the link relative to each other. Say if we say the road and tire of a vehicle is in a contact, the rubbing velocity, when it is in pure rolling, there is no rubbing velocity. The relative velocity of pure rolling wheel in the surface is zero, that we all know that. If it is in skidding, okay, if it is in skidding condition, the difference between two surfaces depends upon the angular velocity of their link relative to each other is called as rubbing velocity. If this rubbing velocity, if it is in the same direction, it is omega 1 is omega 1 minus omega 2 into r. When it is in the opposite direction, omega 1 plus omega 2 into r. And we have a certain notes on the velocity, that is velocity at any point relative to any other point in a fixed link is always zero. That you have to notice that the velocity of any point relative to any other point on a fixed link is always zero, and the velocity of an intermittent point of any link can be found easily by dividing corresponding velocity vector in the same ratio the point dividing by the link. And next one, the angular velocity of a link about one extremity is the same as the angular velocity about others. I hope that you have got some idea about velocity analysis, and now we are going to discuss about the instantaneous center. Wherever the motion of a link, the instantaneous center is happen, we have any point or any link is in a relative velocity, definitely there should be an instantaneous center. About that instantaneous center, the links are supposed to rotate. For your information, if we all know that in our school days there is a huge bill is there, a huge rod is tied up, and we are hitting by some of the rod, it will ring a bell sound. Okay, if you see that, that is kind of a pendulum kind of an action. Okay, if we knock at certain point, the rod, it tend to rotate about the instantaneous center. So that is why we are called as an instantaneous center is good for a link which is moving or rotating. Okay, first of all, we have to know the formula for the instantaneous center. The instantaneous center of a rotating or virtual center. Yes, instantaneous center is also called as a virtual center. Please make a note. Instantaneous center of rotation or a virtual center I is equal to n into n minus 1 divided by divided by 2. That in mathematically we can make this equation as nc2, a complement function of n is a complement function with 2. So what is the meaning is, if I say n is 4, when it is in a complement function, 4 into 3 divided by 2 into 1. Therefore, 4 3s are 12. 12 by 2 is 6. When we substitute the same thing in this formula, if n is 4, 4 into 4 minus 1, that is 3 divided by 2. Therefore, it becomes 6. If we consider this figure, in the direction of VA and VB are parallel to instantaneous center I of the body lies at infinity. If both are parallel, then instantaneous center is infinity. Next, and instantaneous center for the different situation. Let us consider a two link is attached with a turning pair. A two link is attached with a turning pair. The instantaneous center of a pair will be at the point of join or pin join. The figure represents this. The two links, link 1 and 2, are tied by means of a pin, and both are in the turning pair. Like a scissor. We have a scissor, right? On the scissor, we have a two tongs as a two links. The instantaneous center of this point is at the pin joint. And the next, rolling of a sphere in a plane. Let me say a tire or a ball or a football is rolling in a plane surface. The instantaneous center is at the contact point, either a wheel or a ball. Okay, whenever after this concept, whenever you seeing a wheel, a vehicle wheel or a motorcycle wheel, you can easily find the instantaneous center is at the point where the road and tire is getting contact. So that is the thing. Next, when the object is sliding on the plane surface, when an object is sliding on a plane surface, the instantaneous center will be perpendicular to the axis of the sliding component. So we can say it in I alpha. Okay. Next, an object is sliding in a curved surface. When an object is sliding in a curved surface, the instantaneous center will be at the center of curvature of the curved surface. The center of curvature of the curved surface. We say either a hypocycloid or an epicycloid, the instantaneous center for the body which is rotating or moving in a hypocycloid or epicycloid, the instantaneous center is at the center point of the epi or hypocycloids. Okay, so next is an Kennedy theorem. I let you know that by the shortcut of this thing, Kennedy loves ice cream. Kennedyக்கு பிடிச்சது ice cream. So what I'm going to say, we having I, right? What it is means, I means an instantaneous center, and we have a three links. Say L1, L1, L2, and L3. If the three bodies have a continuous relative motion, there are instantaneous center or lies in the same line. Okay, same line, the instantaneous center will having in a same line. For all the three bodies, the instantaneous center are supposed to be, if there is a triangle kind of body, the instantaneous center should be at the middle point. Therefore, the median point having the instantaneous center. Here, I will like to quote an example. If any crank is revolving at a uniform velocity, definitely instantaneous center is at the center point. That is what here we are indicating. If v23 is a translation velocity, it is equal to omega 2 into instantaneous center of 23 and instantaneous center of 12, or we can say it as omega 3 into instantaneous center of 23 and instantaneous center of 13. Next, we are going to discuss about acceleration. Acceleration analysis. The acceleration, we know that the rate of change of velocity with respect to time is called as an acceleration. It acts at the direction of change of velocity. Where the acceleration is happen, if any rate of change of velocity is happening in which direction, on that direction only the acceleration is happens. And we have a different types of accelerations are available. Tangential acceleration, centripetal acceleration, centrifugal acceleration, normal acceleration, and very important Coriolis component of acceleration, or some kinds of an acceleration. Okay, so the acceleration is beautifully postulated by Mr. Kennedy, sorry, Mr. Klintz. He derived an acceleration with uniform velocity. So that we have to see in last. First, we are going to discuss tangential acceleration. The tangential acceleration is the rate of change of velocity in the tangential direction of motion. When we say a wheel, okay, a tire of a cylindrical shape is revolving in a plane, a road or a surface, if there is a translation, if the tire and the road in the contact point they are having a relative velocity, whereas tire is rotating as well as having a translation. The translation is in the linear thing. So this is the rotation acceleration, therefore AR, and this is the translation acceleration AT. In the translation acceleration, how much distance is covered, that we have to notice. Therefore, acceleration A of t is equal to dv by dt, that is dv by dt if there is a rotation into r. Therefore, angular velocity into radius, that is called as an tangential acceleration. Next, centripetal acceleration. Centripetal acceleration we can also call it as a normal acceleration or a centrifugal acceleration, or a resultant or normal acceleration. We can call it as a centripetal or radial or normal acceleration. Both are same. Here, the rate of change of velocity towards the center of rotation, towards the center of rotation. So, if this is a wheel, this is a center point, how much velocity is varying. So, this to this, how much velocity, the omega, it is varying. That we have to notice that. Therefore, centripetal or a centrifugal acceleration is, we call it in omega into r. Whereas the tangential acceleration AT is equal to alpha into r. Alpha is the angular acceleration. So this is angular acceleration. So this is, sorry, here we have to call it as omega square. It is angular velocity square into radius. Okay. And okay, it is towards the center of rotation. It is known as centripetal. When it is away from the center of rotation, it is called as a centrifugal. So nothing changed, only the arrow mark is different. Where this is called as an radial or a normal acceleration. We have to take a note this. In uniform acceleration, the radial velocity and tangential acceleration is 0. When we say in anywhere, if it is having uniform velocity, their radial velocity is 0 and tangential acceleration is also 0. Therefore, tangential acceleration is equal to normal acceleration. Therefore, the total acceleration becomes, total acceleration is nothing but the resultant acceleration. Therefore, A is equal to square root of tangential acceleration square plus normal acceleration square. We know that normal acceleration is equal to r omega square. Therefore, tangential acceleration is equal to r alpha. And we have another note. The tangential component of acceleration occur due to angular acceleration link. The acceleration of intermittent point on the link can be obtained by dividing acceleration vector in the same ratio as the point divided by the link. That we have to know and we have understand that. Next, an important kind of an acceleration which is called as a Coriolis component of acceleration. Okay, wherever the quick return mechanism is there, or wherever the rotation and sliding kind of an action is there, there we have a Coriolis component of acceleration. We can easily see in the quick return mechanism of a shaper or a slaughter, there the rotation of the bull gear is there and the sliding of the crank pin is there. Therefore, the slider crank mechanism, the crank is rotating and the slider is in the sliding motion. Therefore, it is a very good example for making or for understanding Coriolis component of acceleration. We know that the resultant acceleration or Coriolis component of acceleration is equal to square root of tangential acceleration square plus radial acceleration square, where the radial acceleration is equal to v square by r, that is r omega square, where Coriolis component of acceleration is equal to 2v omega, 2 into v into omega. Therefore this omega square will becomes the component of velocity in angular velocity as well as the linear velocity are come into picture for the Coriolis component of acceleration. With the below condition and the example, we can easily understand the Coriolis component of acceleration. When the body rotates and slides simultaneously, that is the condition. Wherever the Coriolis component of acceleration is happening, there that body is supposed to be rotate as well as slide. Okay, for example, if there is a slippery road, okay, or a muddy road, when our vehicle tires, what will happen in our vehicle tires? We are trying to accelerate. If there is a slope, steep slope, we are trying to accelerate. The wheel is rotating due to the lack of friction between the tire as well as the muddy surface. Due to the slope also, it is tend to slide down. Therefore, on that point, the rotating as well as the sliding is happen. Definitely, there should be a Coriolis component of acceleration, where the Coriolis component of acceleration for the sliding vector, it is perpendicular direction. It is perpendicular to the sliding vector, that is inference, that is our inference. The sliding vector, the Coriolis component should be perpendicular, and it is always tangential acceleration. It is always tangential acceleration. It is always available in quick return mechanism. When we say a body is in upward, is by means of the rotation, the body moves upward, that is away from the axis, that is centripetal, then the Coriolis component of acceleration is towards clockwise direction. When it is in downward direction, in the same kind of the clockwise rotation, it is in opposite direction. If the acceleration component is in counterclockwise, it is in the away from the direction, whereas in the counterclockwise, the slow speed, it is always in the downward direction. So with this understanding, we can know what is meant by Coriolis component of acceleration. Next, these accelerations are postulated by Klein's construction. Klein's construction is depends upon of drawing the acceleration polygon. By drawing the acceleration polygon, we can notice what are kind of the acceleration is happening. So Klein's construction denotes the graphical method or a graphical construction of acceleration polygon. It is used in oscillating parts. This Klein's construction are always used in oscillating parts. Used in crankcase in the case of uniform angular velocity. This is about Klein's construction. Okay, I hope that I have given enough knowledge about velocity and acceleration analysis. If you have any doubt, please let me know in the comment section. Thank you all.